Hi passionate scientists, my name is Jorge and today we're gonna solve an electrostatic problem. But before that, let me try to put across some key ideas about this topic. Let's say the electric field inside the conductor must equal to zero. The charge density inside must equal to zero as well, and any net charge inside will tend to go to the surface, yeah? That's clear. Well, so now we're ready to start to analyze or verify these sentences. As you can see, we have a sphere which encloses a charge Q1, look at it at a distance r divided by 2 from the origin of coordinates, and also we have a charge Q2 outside, look at it outside, at a distance square root of 7 divided by 2 and per r. Okay, so now let's analyze these sentences, these statements. Yeah, the force on Q1 due to induced charges at the inner surface is equal to 0. Well, let's analyze that. Yeah, we have a charge here inside, and this charge will induce, as you can see in blue, at the inner surface an asymmetrical charge distribution, yeah, an asymmetrical charge distribution, and and as you can see, there are as many negative charges as positive, and that's because of this, yeah. And what happens at the outer surface? A symmetrical or a spherically symmetrical charge distribution, a positive one, is induced at the outer surface, yeah? But as you can see, we're just asked for the inner surface, so for now we just disregard the outer surface, the charges surrounding at the outer surface, yeah? So as you can see, the charge is not located at the center, therefore the net force is not going to equal to 0, yeah? So this is false. I hope that's clear. Now let's analyze the second sentence. The force exerted on Q1 due to induced charges at the outer surface of the conducting shell is equal to this. So now we have to focus on the outer surface, and as we analyzed before, we have this charge surrounding the shell at the outside, but we don't have, or not just, we have to focus on these charges, but on Q2, yeah? Under no circumstances should we forget about it. And always we're working, or at the point we're working with the charges, the positive charges, or at the point we're working with spherical symmetrical shell, we have to remember, or the following statement must come to our minds, yeah? And I quote Newton's theorem shell, or shell theorem, yeah? And this one says that when we are working with this kind of shell, the net force, or not net force, neither electric or gravitational, is exerted by the shell on any object inside, yeah, regardless of the position of this object inside, yeah. So we forget, because of that, yeah, we forget about these charges surrounding at the outer position, yeah. So we focus on Q2. What happened with this charge? That's gonna induce an asymmetrical charge distribution, pointed out in red, yeah. And what happens with this? That this charge is gonna experience a force is gonna be exerted by these charges on this charge inside. Firstly, there is let's calculate first the negative charge, but before calculating anything, let's point out that this shell is regarded as a Faraday cage. What does that mean? That the electric field, the net electric field, the total electric field inside the conductor must equal to 0. And because of that, the forces must cancel out. Yeah, must cancel out. So let's analyze that. Firstly, let's calculate the attractive force. Yeah, the attractive force. Let's see. Yes. Yeah, we have K, Q1, Q2, and R. What's the distance between both charges? Let's calculate them. Let's compute them. Yeah, we have this, and as we know that this is equal to this. Yeah, this is just simple calculation. Sorry. And this is equal to 2r squared, yeah, if I'm not mistaken. Yes. So now we know that the attractive force will equal to Q1, Q2, to yes. You know the K, okay, so yeah, it's 8. Yeah, that's correct, yes. So we have the attractive force, but the attractive force will equal to the repulsive one, but with a negative sign right here, because that's the reason of this is because we're working with a shell that is regarded as a Faraday cage. Yeah, that's clear. So this is true. Yes. So once we have calculated that, those statements are easily proven. Yeah. So the force on Q2 due to induced charges at the inner surface is equal to 0, or is equal to this result that is the same. Yeah. Because we are giving the absolute value. Yeah. So we're given the absolute value in case we are taking the repulsive force. I regarded the repulsive force as the negative one. We'll take this value, or we just explain it. Yeah, I think that's really clear. And now, what happens here? That we have to verify this. Yeah, but as you can see, we don't have to calculate anything else, as we have the same case that here. Yeah, the force, there is a force. Why? Because at the inner surface there is an asymmetrical charge distribution. Therefore, there is a force. Yeah, there is a force, and it's not equal to 0 because of that's why, or the reason why that is like this is that Q1 is not located at the center. Yes, as I said before. So we have a symmetrical charge distribution, and the force is not equal to 0, and this is false, obviously. And what happens with this? This is true, because we just calculated this case, but just working with the outer asymmetrical charge distribution induced by Q2, but this time we're working with the asymmetrical charge distribution induced by Q1. So it's the same case, but now we're working with the inside one instead of the outside one. I think that's clear. So thank you for your attention in this video, and see you soon with new ones. Keep working. Bye.